Good afternoon. I'm Xiaomei Wan from Qingdao University of Technology. The title of my presentation is Fracture Toughness of Ultra-High Toughness Geopolymer Composites based on double K criterion. The presentation involves 4 parts: background, experimental, results and discussion, and conclusions. Ultra-high toughness geopolymer composites is a new type of building material with sustainable and high performance. It's a class of geopolymer-based materials typically reinforced by PVA fibers. The main advantages of UHTGC involves high strain capacity and tensile strength, high toughness and crack control capability, strain hardening and multiple micro cracks, steady-state cracking mode. Fracture toughness provides a criterion for interpreting crack resistance of concrete under different loads. Furthermore, the degree of crack propagation is determined by fracture toughness, which has important significance for analyzing the performance of concrete. Xu and other researchers proposed a resistance curve Kr based on crack cohesion and the double K fracture model, which solved the problem of characterization of the whole process of concrete fracture. In this work, an ultra-high toughness geopolymer composites were fabricated, and the influence of slag content and pre-curing temperature on fracture properties were studied. The research contents involves tensile properties, fracture toughness, micromechanical properties, and microstructure observation. This is experimental. A fly ash and a granulated blast furnace slag were selected as the binding materials. A mixture of water glass and sodium hydroxide solution was used as alkaline activators. A coarse sand with a maximum particle size of 600 mm was applied as fine aggregates. The 2 tables are chemical composition of binding materials and the properties of PVA fiber. 6 mixes of geopolymer and geopolymer-based composites were prepared. That's the mixed proportion, from M1 to M6. Among them, M1, M3, and M5 are the specimens reinforced by fiber with 2%. Each specimen with molds was placed in 3 temperature environments as 20, 60, and 80 centigrade for 12 hours respectively. The tensile properties and strain hardening behavior of specimens were analyzed based on the tensile strain stress curves obtained through the uniaxial tension test. The left figure is a dimension diagram of dumbbell specimen, and the right figure is the loading process of the tension test. In order to obtain the parameters for calculating fracture toughness and fracture energy, 3-point bending tests of notched beams were carried out. This figure is a mold for preparing notched beam, and this figure is the picture for the notched beams, and the right one is loading process of 3-point bending test for notched beams. The elastic modulus and hardness of nanoscale were obtained by nano indentation test, and the fracture toughness of nanoscale was obtained by loading-unloading diagram. This is the samples for nano indentation test, and the right one is the instrument, the machine of nano indentation test. Then let's come to the results and the discussion. These are the strain stress curves of specimens with 2% fibers. 20, 60, and 80 means pre-cured with certain temperature. We can find that the strain of composites decreased generally with the increase of slag content and pre-curing temperature. When the tensile strength is high enough, the fiber feeder mode is changed from pull-out to breaking. When slag content is 20%, the strain of composite is enhanced except for the one under the pre-curing temperature of 20 centigrade. Other mixes show a low strain but still behave hardening performance. Proper but not high slag content is benefit for the strain hardening of the specimens. Let's look at the relation curves of load and crack mouth opening displacement with and without fibers. Then the double K fracture toughness parameters are derived from the above curves, and the fracture toughness are shown in the right figures. We can find the initial fracture toughness and unstable fracture toughness of specimens with PVA fiber are higher than those without fiber, while the initial fracture toughness and unstable fracture toughness of M1 specimens are slightly lower than those of other mixed proportions with fiber. This table is the fracture energy parameters obtained from the load deflection curve of notched beams under 3-point bending load. We can compare the two figures. This one is fracture energy of specimens with fiber, and the right one is from the specimens without fiber. We can find the fracture energy of the specimens with fiber is 17 to 77 times that of the specimens without fiber. For the fracture energy of non-fiber specimens, the increase of pre-curing temperature and slag content will lead to decrease of fracture energy. For specimens with 2% PVA fiber, the fracture energy increases with the pre-curing temperature enhanced from 20 degree to 60 degree, while decreases with the curing temperature enhanced from 60 degree to 80 degree. Here is the results of nano indentation results, which are in good agreement with the macro test result. With increase of pre-curing temperature, the modulus of elasticity increases while the fracture energy decreases slightly. The fracture energy obtained by 3-point bending of notched beams is weaker than that obtained by nano indentation tests. It's mainly due to the anticipated size of cracks in the test of 3-point bending notched beams, the damage in demolding, and the errors in the test process, which will greatly reduce the fracture energy obtained. Then let's come to the conclusions. With proper content of slag and pre-curing temperature, the average strain of the composite under uniaxial tension load attains to 3%. Increased content of slag is not conductive to the increase of strain. The ductility first increases and then decreases with the increase of pre-curing temperature generally. For both initial fracture toughness and unstable fracture toughness, UHTGC is higher than the specimens without fiber. Before unstable cracking, the specimens undergo a stable significant deflection during which the crack length expands continuously. The fracture energy of UHTGC is 17 to 77 times of that of mixes without fiber. The modulus of elasticity increases with pre-curing temperature, while the fracture energy decreases slightly with curing temperature, which are similar to those of macro-scale mechanical test results. That's all of the presentation. Thank you.